Hey everyone, it's Mr. Anderson here, and today we're getting together to talk about section 8.1.2 from our Common Core Algebra CPM ebook, and we're going to look for some patterns in factoring today that allow us to maybe get a little leg up time-wise, right? A little bit of a shortcut. We're going to try to answer this question, and we'll do so using our work from section 8.1.1. So if you haven't yet seen the 811 video, it's a must watch before we watch this one. So go back, take the time, and watch that prior to engaging in this video. Math is often described as the study of patterns. As humans, we're really, really good at recognizing patterns, which is why math is sometimes a pretty natural fit for some people. And just like a lot of other patterns that we see, generic rectangles have patterns. So let's start there. We've got a generic rectangle here in problem 8-13. And we've got the generic rectangle, and we want to write the area and sum as the area as a sum and a product. So real quick, the first thing I'll do is I'll start by writing it as a sum. And I see a 10x squared. And then on the tail end, I see a 14. So I've addressed the 10x squared and the 14. The reason I didn't write the middle term yet is because recall some of the things that we've seen so far inform us that those like terms can and should be combined. So I'll put those two things together. I ask myself, what's negative 35x and negative 4x? Well, together they make negative 39x. Okay, so I'll just add those two things together and write them as one term. Okay, there's my area as a sum. But now, in order to write it as a product, recall we write this as the product of two binomials. So I'm going to go here and I'm going to start to ask myself some of these questions that we saw in section 811. So what two numbers, when I multiply them, make 14? Now, there's a couple factor pairs for 14. 14 and 1 and 7 and 2. Because I see 35 and 4, and I know that 7 goes into 35, and I know that 2 goes into 4, I'm going to guess 7 and 2, and I'm going to put them here like that. Now, I may not be perfectly right, but I might be on the right track, so to speak, okay? And then I need to start thinking of, okay, well, what kinds of things allow me to make 35, right? And I'm not worried about the sign yet. We'll get there in a second, all right? I know that if I multiply, sorry about that. I know that if I multiply 7 by what number, what gives me 35x? Well, I know 7 times 5x gives me 35x, okay? And then I know, what number do I need to multiply 2 by to get negative 4x? Well, that's got to be a 2x. Now, here's the kicker for me. Check this out. All right? It's true that 5x and 2x, when I multiply them, they give me 10x squared. So we're good there. Check. And it's true that 7, when I multiply it by 2, gives me 14. So we're good there. Check. The problem is, it doesn't give me a negative 35 and a negative 4, okay? Negative 35x and negative 4x. So what's one way that I can still accomplish that? And recall from some integer arithmetic that a negative times a negative is, in fact, a positive. And look what this does. This means that 5x times negative 7, that does give me negative 35. So that's working. All right, and that negative 2, times 2x, that gives me negative 4x. That's working. So I'm good there and there. I erase that check mark. Okay, but it's also still true that negative 2 times negative 7 does give me positive 14. So I've got a product here that's going to work out, and that product is 2x minus 7, and then finally 5x minus 2. Okay, and that's going to work out really, really well for me. All right, so we're in good shape. I've got the sum as an area, I've got the sum as a product, and of course we're asked in part B, does this generic rectangle fit Casey's pattern for diagonals? And the pattern we saw yesterday is asking us the question, hey, does that product equal that product? So the question we're asking is, what is 10x squared times 14? And that works out to be 100 and 40x squared. All right, and then the other question, of course, is what's negative 35x times negative 4x? And that's also positive 140x squared. So it does fit that pattern. We are seeing that one more time. Okay, to develop a method for factoring, right, we're going to put ourselves in a position to do some factoring here with algebra tiles. We're going to talk about how we model this, and then we're going to look for the connections within the rectangle, okay? Watch how this works out here, and I'm going to use this e-tool here, and this is a clickable link. We're going to factor 2x squared plus 5x plus 3, and we're going to look for connections in that generic rectangle. So I click it, here I go, and the only thing that I'm going to modify here is I'm going to modify, it's not going to allow me to modify that background. Oh, that's okay. I normally would put in the corner background, but just like we've done historically, I'm going to go ahead and I'm going to put those x squareds in the corner. I'll start there building my rectangle. Now, if I just start to line these up, it's generally not a good idea to line them all up at once like this. Obviously, I can't evenly distribute all of them across the top and have it work out. But if I line them all up here, I'm going to run out of room with these ones. So I'm going to just consider what happens if I take, and I got to rotate these. Double click, maybe. Oh, it's not working. I can't, there we go. I rotated it. Okay, and I'm going to rotate one more and stash it sideways. And you guys are going to see this work out, I think, pretty gosh darn nicely. All right, so I do that, and then I do that. Now look at this. I've built a rectangle. So I've got my 2x squared, I've got my 1, 2, 3, 4, 5x, and I've got my 3. That's the area as a sum. But how does it connect to the area as a rectangle? Well, watch this, right? Watch how I'm going to write this. But first, I guess I'll draw it. Okay, check this out. Okay, and I'm going to try to do this. Try to draw it. There we go. Let's see, like that, and then 1, 2, 3. Okay, 1, 2, 3, and then it goes like that. Okay, so I've got an x squared, I've got an x squared, I've got an x, I've got an x, I've got an x, an x, and an x, and then I've got 1, 1, and 1. Now, how does this fit along with the generic rectangle? It's going to be a 2 by 2. Right? This trinomial is going to factor into 2 binomials. I'm going to take these, group them together. Watch this. It kind of fits right here, 2x squared. And I'm going to take these, put them together, and that's just a 2x. Take these, put them together. That's a 3x. Take these, put them together. And you can kind of see that natural quartering, and it's not a perfect quarter. Quarter is the wrong term, but I've got a quadrant style format that kind of divides that up and creates a factorization for me. Okay, now what does this mean? Well, it means I've got x, and 1, and 1, and 1. That's 2x and 3. Okay, and then I've got x and 1. That's x and 1. So my area as a product is going to be 2x and 3 and x plus 1. And that's how algebra tiles can really help us factor. Okay? To factor with, and I'm looking at B now, to factor with the tiles like we did in part A, you need to determine how many tiles need to be arranged to form a rectangle. Using a generic rectangle to factor requires a different process. Miguel wants to use a generic rectangle to factor 3x squared, 10x, and 8. He knows that 3x squared and 8 go into the rectangle in the locations that we have shown here. Finish the rectangle by deciding how to place the 10x terms. Well, here's how we've got to set this up. I've got to put the 10x's in here somewhere. Okay, and the thing that really helps me is if I do some realizing that like 3x and 1x are my factors of 3x squared, but I also need to consider how I can make my factors of 8 work for me. Okay, so if I was to use like 1 and 8, just give me some tolerance here. And I was going to put the 8 here and the 1 here. Now look at this. 8 times 3, that works out to be 16, and 1 times 1, that works out to be 1, and I guess x, sorry. That's way too many x's. So I really need to start to consider how I can work this out. And if we remember that rule that says, hey, I've got 3x squared times 8, that's 24x squared. This, when I multiply this other diagonal, also needs to be 24x squared. So how do I break up 24? Oh, that's right. They need to add 10. How about 6x and 4x? Okay. Now you can probably see already that I've got those in the wrong spot. And how do you know what's the giveaway? That 3. 3 doesn't go into 4, but it does go into 6. Let me show you what I'm talking about. If I put the 6 here and the 4 here, now this can be 3 times what number gives me 6? Oh, 2, that's right. And 1 times what number gives me 4? Oh, that's right, it's 4. And now, of course, final check. 4 times 2, that does give me 8. So that works out pretty well. I can write this then as a product 3x and 4. Sorry, plus 4, and then 1x plus 2. Okay, so that works out pretty well, and it's gonna work for you no matter what you need it for. Kelly wants to find a shortcut to factor 2x squared, 7x, and 6. She knows that 2x squared, sorry, go into the rectangle, and she also remembers Casey's pattern for diagonals. Without actually doing the factoring, what do you know about the missing 2 parts of the rectangle? Well, I kind of already gave it away in part B. Those missing 2 factors need to have a product of 12x squared. So what are the factors of 6 that we can use? I'm sorry, check that, I misspoke. What are the numbers that sum to 7x that we can use that have a product of 12? And they are going to be 3x and 4x, right? Because those 2 things add up to 7, and those 2 things work out to have a multiple of 12. Okay? All right, and we can spend time lining those items up, right? Like, for example, this could be like 2, and I don't know where they go yet, 2x and 1x, and then this could be 2, well, that's not going to work there, all right? So this could be 3, I guess, and if that's going to be a 3, I guess maybe I got to rearrange here as well. This could be a 2, a 1, and then this could be a 2, and then this, of course, could be a 3, and now everything should work out. All right. To complete Kelly's generic rectangle, you need to find the 2x terms that have a sum of 7 and a product of 12x squared. Create and solve a diamond problem that represents this situation. Well, I think you can now start to see the connection of those diamond problems. So we need 2 things that multiply to be 12x squared and have a sum of 7x, and of course I already kind of gave you guys that information, 12x squared, sorry, gave you guys that information that those are the ones that we are looking for. All right, use your results from the diamond problem to do that factorization, and they are there. It is 2x and 3 and 1x and 2. And that's the way that one's going to look out. Okay? We can continue to factor, and factoring with that rectangle is really pretty gosh darn convenient. And I'll try to sneak one more factoring problem in here before we end this video. When we're going to go ahead and factor this trinomial, what 2 parts can we always sneak in there? Well, you can always sneak in there those terms that didn't get combined. All right, so I'll put in there the 6x and the 12. It's our first and last. And then what I need to do is consider the multiple of these 2. Those 2 things multiply to be 72. And now I need these 2 things to add up to 17. And the 2 numbers off the top of my head that I know multiply to be 72 and add up to 17 are 8 and 9, and I'll include x's on there. And now it's all about arranging things so that I know I can get a 12 and a 6x squared. So I'll, for example, put a 3 here, I'll put a 4 here, and then 2x times 4 is 8x, 3x times 3 is 9x, and now I've got that thing writable as a product. Okay, so what does that look like? That is going to be 3x plus 4, and finally 2x plus 3. Folks, there is a tiny bit of review preview at the end of this section. It is 17, 20, 21, and 22. Try these things so we know what questions we have. Ladies and gentlemen, I appreciate you watching. Have a great day.